Okay, the diagram shows a rod attached to a wall by a hinge and a string. A 9.6 kilogram block hangs at the end of the rod, but the rod remains horizontal. The mass of the rod is negligible. Calculate the tension in the string. So we're trying to find the tension that's acting along the string like this, pulling on the rod, and this mass here is pulling on the rod as well with its weight. Where should we take moments about? Okay, because there's going to be a force on the rod from the hinge and the wall here, and we don't know what that force is and we're not interested in it, we should take moments about the hinge so we can ignore that force. Okay, so taking moments about this, some clockwise moment will equal some anti-clockwise moment. The clockwise moment is going to be created by this mass trying to spin it that way. The anti-clockwise moment by this tension in the string here. So the clockwise moment is going to be from the weight of the block, so it's going to be 9.6 kilograms times 9.81, which is the gravitational field strength, times the distance from the hinge to that point, which is 1.8. That gives us 169.5 Newton meters. The anti-clockwise moment is going to be from the tension string, but not all the components from the tension string is actually going to cause a turning effect, an anti-clockwise. It's only this component here, which is the opposite part. Okay, so we're going to have to use T sine 40. Okay, so T sine 40 is the force, and the distance to that point is 1.2. Okay, so now I'm going to make these two equal. So if I make that equal, we'll get 169.5 is equal to sine 40 times 1.2 is 0.7713 times T, and solving for T you get a tension of 220 newtons acting along the string. Okay, calculate the force on the hinge. Now I could take moments about a different point and try to calculate the force on the hinge, but it'll be quicker if I just use resultant force equals 0. But it's a bit more complicated this time because this force here is at an angle. So not only will there be components that I need to balance upward and downward, but also towards left and right. So if I resolve this tension, I get two components, one towards left, one upwards. The one towards the left, well, this is the only force that's towards the left, and so there's going to have to be a force from the hinge acting towards the right to balance that. So 168.5 newtons from the hinge acting towards the right to balance that. And if we look at the upward force, 141.4, and the downward force, we can see the upward force is bigger. So there's going to have to be a downward force on this one, and we can figure that out by doing 141.4 minus the 94.18, and that gives me 47.22 newtons, which is going to have to act downwards. 47.22 newtons. So overall force is going to have to be acting this way. To calculate the magnitude and size of that, I can use trigonometry, and then also I know that if I define this as theta here, I can use tan inverse of opposite over adjacent to figure out the angle there, theta. If I do that, I get an angle of 15.7 degrees. A uniform ladder of 5.0 meter rests on a smooth wall. Okay, so there's not going to be any friction from the wall on the ladder. It's just a normal reaction force. The mass of the ladder is 15 kilograms. Okay, because it's a uniform ladder, the mass, or the center of mass, is going to be halfway, which is 2.5 meters up the ladder there. Okay, the bottom ladder is 60 degrees above the floor. Determine the force on the ladder from the wall. Okay, well, I'm going to take moments about x here at the bottom. Okay, so this is because it's obviously going to be a force from the floor on the ladder, and I'm not interested in that, so I want to ignore the effect of that. So if I take moments about x there, I'm going to figure out the clockwise moment first. So the weight of the ladder is going to spin it clockwise, and the normal reaction force is going to spin it anti-clockwise there. So if I'm interested in the weight of the ladder, of course there's an angle here, so I'm going to draw the line of action of the force here and use a perpendicular distance, which is this here. Okay, so I'm interested in that part, and that's adjacent to the angle there, 60 degrees, so I'm going to have to use cosine. Okay, so 2.5 is the distance, and I'm going to use cosine to get the perpendicular distance, so cosine 60 there, and then multiply by the force, the weight of the ladder, which is 15 kilograms times 9.81. That gives me 183.9 Newton meters. Okay, what about the anti-clockwise moment? So that's going to be from the reaction force. Okay, so if I draw the line of action of that, and the perpendicular distance is going to be this. Okay, which is if we draw this as 60 degrees here, because that's an alternate angle. We're interested in the opposite now. Okay, so that anti-clockwise, the normal reaction force times the 5 times sine 60. Okay, so that is 4.33 times the reaction force, and if I balance this, so 4.33 times the reaction force equals 183.9, and I solve for R. Either R is equal to 42 newtons. Okay, add an arrow to show the direction of the force from the ground on the ladder at point X. Okay, so we're still going to use the idea that the resultant force equals 0 to figure out the direction of the force at point X. Okay, so we know the normal reactive force acting towards the left like this, and the weight is acting downwards. So I need another force which is going to balance these two forces here, one force at point X. So I know that if it's the resultant force is equal to 0, if I add the forces tail to tip, that should form a closed shape. So the missing force that I need to add is this one here. Okay, that forms a closed shape, and that means that the resultant force is 0. So the force at point X is going to be acting somewhere like this. Okay, and all the forces are balanced.